Welcome to Blueprint Education Labs. Today, we are mastering a cornerstone of spatial computing, the Z-order curve. In an era where billions of devices generate location data every second, from GPS pings to satellite imagery, efficiently managing multidimensional information is no longer a luxury. It is a fundamental requirement for the modern web. Before we look at the math, let's understand why this matters. We live in a world of multiple dimensions: longitude, latitude, altitude. But our computers are fundamentally one-dimensional. This mismatch is what we call the spatial paradox, and today, we're going to solve it using one of the most elegant mathematical patterns ever discovered. Look at this map. Every point represents a piece of data: a coffee shop, a driver, or a sensor. When you open an app and search for what's nearby, the computer must instantly find points that are geographically close to you. In our human eyes, closeness is a simple 2D distance. But for a computer, the concept of a nearby coordinate is a massive technical hurdle. There is no such thing as a 2D address in a CPU. To a processor, everything is just a sequence of numbers, and finding proximity in a flat grid requires a level of translation that most software developers take for granted. This hurdle exists because your computer's RAM is just a long, linear line of storage addresses. 0, 1, 2, 3. In a single, never-ending file. There is no up or down in a memory chip. There is only before and after. To store a 2D map, we have to flatten it into a single straight line. The goal is simple. We want to map 2D coordinates to 1D addresses such that points that are neighbors in the real world remain neighbors in the memory chip. But as we'll see, the traditional methods of doing this are surprisingly flawed. The traditional way to do this is row-major order, where we store the grid row by row, like reading a book. But this destroys locality. Watch as we unroll this grid. The cell directly above you is your neighbor in space, just 1 pixel away. But in memory, it's pushed thousands of addresses away, exactly 1 full row length. You might wonder, can't the cache just load the bottom line as well? Technically, yes, but CPU caches load data in cache lines, contiguous blocks of memory. To fetch a vertical neighbor, the CPU must jump across the entire row, performing a slow random access instead of a fast sequential read. The Z-order curve, or the Morton curve, is our solution. Proposed by Morton in 1966, it weaves a single, continuous line through the grid in a recursive Z-shaped pattern. This ensures that points that are close on the map stay close in memory, regardless of whether they are horizontal, vertical, or diagonal neighbors. But the real genius isn't just the shape, it's how we calculate these addresses. Instead of complex trigonometry or expensive lookups, we use a technique called bit interleaving, which uses the very binary structure of our coordinates to preserve their geography. Let's look at the bit-level transformation. Take coordinates x equals 5 and y equals 3. In binary, x is 101, and y is 011. To find the Morton code, we zip these bits together like a zipper on a jacket. We take 1 bit from y, then 1 bit from x, alternating all the way. The resulting binary code is 1-0-0-1-1-1, which equals 39 in decimal. This operation is incredibly fast, requiring only a few CPU cycles, making it ideal for real-time applications. To see why this forms a Z-shape, let's look at a 3-bit grid. Every cell's address is the result of interleaving its x and y coordinates. The first bits decide the major quadrants, and the last bits determine the micropositions. As we follow the binary sequence from 0 to 63, the path traces a series of small zs that combine into larger zs. This recursive self-similarity is the defining characteristic of the Morton order. Every cell is uniquely identified by a binary string where the even bits are y and the odd bits are x, pinning every point to a specific UN crossing sequence. This zipping creates a beautiful spatial hierarchy. The first 2 bits of the code decide which of the 4 major quadrants you're in. The next 2 bits decide which subquadrant you occupy. Every pair of bits you add narrows down your location in both dimensions at the exact same rate. We are building a map within a map, recursively. This hierarchical nature means that the Z-order curve is essentially a linear representation of a quad tree. A database can find a whole cluster of data by reading a narrow, contiguous range of memory addresses, significantly reducing I/O overhead. Now, consider the power of range queries. If we want to find all points within a specific bounding box, say, all Uber drivers within 5 blocks of your location, the Z-order curve allows us to translate that box into a set of linear memory ranges. We use a powerful algorithm called getNext. When the curve leaves our search box, we identify the LITMAX, the largest Morton code in that segment still outside our box. We then calculate the BIGMIN, the smallest Morton code after LITMAX that lands back inside. The computer jumps directly from LITMAX to BIGMIN, skipping irrelevant data points instantly. We will have another dedicated video to dive deep into the math of LITMAX and BIGMIN. But for now, remember that they are the key to surgical precision in search. Let's step into the getNext algorithm in detail. We start with a 4x4 grid, just 16 Morton codes. Our query box covers cells at Xset membership symbol 1, 2, Yset membership symbol 1, 2, which translates to Morton codes 3, 6, 9, and 12. Now, watch the cursor scan from code O. Codes 0, 1, and 2 are outside the box. We scan them quickly. Code 3 is inside. We have our first result. Now the cursor moves to code 4, which is outside. Instead of scanning 4, 5, and then discovering 6, the getNext algorithm asks, what is the LITMAX? It is 3, the last code before we exited the box. And what is the BIGMIN? It is 6, the earliest code guaranteed to be back inside. So the algorithm jumps directly from code 3 to code 6, skipping codes 4 and 5 entirely. This is the getNext algorithm in action. At scale, say, a 512 by 512 grid with millions of queries, these jumps reduce search time by orders of magnitude. The LITMAX and BIGMIN are computed entirely from bit operations, making each jump as fast as a single CPU instruction. You might be wondering, is the Z-order curve the latest or best method? Many modern libraries like Google's S2 actually use the Hilbert Curve, which was discovered back in 1891. While the Z-order curve is much faster to calculate, the Hilbert Curve offers even better locality because it never makes long diagonal jumps. However, for most high-performance systems, the sheer simplicity and speed of bit interleaving makes the Z-order curve the preferred choice for massive scale indexing. We'll be doing a deep dive into the Hilbert Curve in a future video, so stay tuned for that. Let's watch the curve form as we increase the precision to its theoretical limits. At 1 bit, we have a simple 2x2 grid. But as we add bits, the grid grows exponentially, and our Z-shape replicates and connects into a deeper, mesmerizing fractal. At 8 bits, we have a dense 256 by 256 resolution. That's over 65,000 unique addresses stored in a single linear line. Watch the yellow point as it traverses the path. No matter how dense the grid becomes, the point always follows the same recursive logic, never crossing itself and always staying local to its neighbors. This is the magic of the Z-order curve. It turns infinite 2D complexity into a simple, searchable 1D line. The Z-order curve is the silent engine of modern spatial logic, powering real-time location services, cloud databases, and geospatial analytics at massive scale. It is the perfect example of how an elegant mathematical pattern can overcome the physical limitations of hardware. As Alfred Korzybski famously said, the map is not the territory, but if correct, it has a similar structure, which accounts for its usefulness. At Blueprint Education Labs, we believe that understanding the foundations makes you a better engineer. We hope this deep dive has helped you fold complexity into clarity. What other concepts should we explore? Let us know in the comments. Thank you for building with us today.